So, hello everyone, thank you for coming to this session. I really appreciate it. So today I will talk about a little bit about the application of fractal geometry to estimate the stand or tree volume. And I need to explain a little bit what is a fractal because some of you are looking a little bit weird about that. So fractals are a geometric structure whose shapes tend to be conservative. You observe that at different scale. An example of this could be, for example, this cube filled of cubes. These leaflets that you can find in a fern, or some chunks or branches that you may see in a tree. So these have several applications in plant ecology and plant forestry, and the main reason for that is because the fractal relationship that you can find in plants are strongly related with the power law, which describes the allometric scattering of plants. So in point clouds specifically, fractals have been applied to the structural indication points when you have scenes, when you have scenes composed by buildings and trees. But also using TLS point clouds, it can be used to characterize the tree and stand complexity. And in few cases, can be used to characterize the tree metrics, for example, tree height from diameter. But never before, it can be used to characterize the volume of geometry in a given tree, or also the volume of a given stand. So our goal is to explore this kind of application. So for this, we use databases of point clouds of trees that are distributed around the world. Before I continue, I need to say thank you to all the authors who share their data in open access repositories. So, and this database consists in point clouds of trees with leaves and point clouds with trees without leaves, for a total of 49 species and 23 families. So on these point clouds, we derive metrics associated with tree height that we displayed in some slides, and also we extract metrics associated with the fractal dimension. So the metrics that we extract from 3 point clouds were tree height, like using a standard approach, then the DBH using cylinders from a part of a tree. Also the crown area using a modification of convex hull or a top view of a tree. And also the tree volume using the approach or harmonic of QS and volume. And for that, then we derive also the fractal geometry. And the fractal geometry is basically that you have a point cloud, you can use a bigger voxel to fill this given point cloud. But when you start to reduce the volume of those voxels, more voxels you will need in order to fill it. So this relationship follows a power law that can be used, can be explained, for example, by the number of voxels and inverse the voxel size. And from this we can get the slope that will represent the fractal dimension, and also we can get the intercept that will represent the capacity state. So we use these two parameters and we regress those against the three metrics in order to see their relationship. So in the first result, when we start to see the relationship of the fractal dimensions with three metrics, we observe that the relationship is tend to be really poor. And this is a little bit disappointing, but when you start to see this distribution of points, it's possible to see that there are some point clouds that present leaves and doesn't present leaves that tend to be separated between them. So it seems that when we have a point clouds with trees with leaves, the point clouds of trees with leaves, it seems that the complexity tend to behave different, and you can do a separation of, or you can distinguish if a point cloud has leaves or not. On the other hand, if we take a look to the intercept, these tend to have a strong relationship with the three metrics. Specifically, if we take a look to the volume, which is the main interest of this presentation, these tend to have a really strong relationship between them. If we take a look more deeper in just in this part here, the blue dots, and we observe the differences between, if we compare the slope between databases, we found that this slope don't differ between databases. That means that this approach can tend to be consistent if we use point clouds from different sets. So, can we apply this, for instance, So that was our next question. This is quite difficult to have point clouds of stands because you need to have several plots. So we came with an idea that we call artificial stands, and that is adding trees to a given plot. How this works? So let's assume that we have a given area, and then we can have a point cloud, and we can locate that point cloud in this plot. And we can use that with using 2, 3, 4, or whatever number of points. But at some point, if you have a point cloud that overlap with an existing point cloud stand, that is not located in the current stand, and they provide a new location until they may fill an empty space. So from this, if we have a library of points, if we have a library of points, we can select a random number of trees, and we can select a given area, and we can create a stand, for example, of 20, 50, 80, or even more trees. And then these stands will look like this, and may appear a little bit like a bullet. But the most important of that is that we can apply the voxel-counting approach that we derived, that I explained before, and because we have an identity of each point in this stand, we can derive stand metrics. So we can compare the relationship between them to see how the variation of this relationship. So we do these artificial stands 1,300 times, several times, and we see how the pattern. So what we found again is that this fractal dimension seems that it doesn't have a relationship with stand metrics, and this relationship is also not affected. We see that it's not affected by a number of trees that is represented with this called gradient. But if we take a look to the intercept of that, it seems that the intercept tend to predict pretty well what is the stand metrics. So the next question for that is, can we use this slope? How is this slope in comparison to the slope that I presented before? So we did comparison slopes using the standard elevator axis, and what we found is that this slope do not differ when we compare with a single scan approach. So this is pretty amazing, because this may represent that we can use a single equation not just to predict the stand volume but also a tree volume. And that's something we have a lot of room to improve that. We need to test that in real stands. But I think this is a good approach to estimate the volume of stand based on fractals. So some conclusion of this is that fractal dimension seems to predict the presence of these in 3-point clouds. Likewise, the variation by intercept is strongly associated with 3 metrics. Then, the fractal dimension stand level doesn't seem to predict, or doesn't seem to be associated with a number of trees. And we need to explore a little bit what is the effect of gaps, or what is the effect of clumping of trees on this fractal dimension. And then the intercept seems to predict some metrics. And those are represented by these equations. So there is a lot of room for improvement over this, and we are exploring that on real plots. Also, we want to look what is the effect of the presence of this fractal dimension, and what is the effect of the presence of other elements like lianas or columns or ferns on this kind of system, and how that can be affect the fractal dimension that we may have in our given forest. So I would like to thank you to all the authors who shared the databases, databases, repositories, and also organizations who funded this research, especially to Sorky Cry, Bang. So thank you so much.